Linear programming is largely just the generalization of this sort of problem solving to n dimensions, instead of just the 2 that we've seen so far. We can write our optimization problem in a form like this one. In matrix form, this becomes maximize C transpose x such that AX is at most B and X is non-negative. Note that inequality, when applied to matrices, means that it holds for each element in the matrix. When we first encounter a linear programming optimization problem, it might not be in this form. In fact, the only requirements for an optimization being a linear program is that both the objective function and the constraints be linear, whether they're inequalities or equalities. If this is true, then we can always turn it into a canonical form like this one. Here are the key transformations. To convert a max problem to a min problem, or vice versa, just negate the vector c, which contains the coefficients for the objective function. Thus, max C transpose x becomes minimizing negative C transpose x, and minimizing C transpose x becomes maximizing negative C transpose x. To convert an upper bound to a lower bound, or vice versa, in one of the constraints, we simply negate the inequality. We can convert an equality into two inequalities by giving both an upper and a lower bound constraint. Here I've played the trick from transformation 2 to make these both at most constraints. Things get a little more interesting when we go from one of the inequalities to an equality. Here we introduce a new variable, either a slack or a surplus variable, depending on the inequality. There's also the problem of free variables that are allowed to be negative. There are two ways to cope with one of these. If it is involved in an equality constraint, then we can often simply eliminate it through substitution. Otherwise, you can replace it with two new non-negative variables and just substitute the difference for x everywhere.